one, not two, but three useless pieces of paper. Amazing. Okay, so what are we doing today? 2125 number of laser beams in the bank. Beep, beep. We're gonna be bank robbers today. That's why I'm wearing this outfit, you know. Little robbery action for you guys, you know what I'm saying? You know, I'm gonna solve the whole problem like this, and you're probably gonna have difficulties hearing me because it's gonna muffle the sound waves from my voice into the microphone. But here we go. So anti-theft security devices are activated inside of a bank. That's good. You are given a zero-index binary string array bank representing the floor plan of the bank, which is an m by n 2D matrix. All right. Bank I represents the ith row consisting of zeros and ones. 0 means the cell is empty, while 1 means the cell is a security device. Okay. There is one laser beam between any two security devices if both conditions are met. The two devices are located on two different rows, R1, R2. And for each row, where R1 is less than R2, there's no security devices on the ith row. Laser beams are independent. One beam does not interfere nor join with another. Okay, like, you know, this right here. Return the total number of laser beams. Okay, so what I'm going to do is I'm going to reverse engineer this. Reverse engineer. It's always funny how you can use, like, super sophisticated words to say the most simple things, and people assume that is some sort of indication of intelligence. I'm going to reverse engineer this image. It's a terrible habit that I've learned from the working world, right? People using, they don't call them PowerPoint presentations, they call them slide decks. Oh, this is my slide deck. Oh yeah, I'll share you the slide deck. Oh, my tech deck, slide deck. Anyways, so this image really is derived from this array, right? So 1, 1, so 1 represents that there's a device there, right? This whole row is empty, which will become important in a moment. There's a device here, a device here, 0, 0. Right, so this is just, you know, a binary, 0, 1 representation of the actual laser scheme in the system, right? And you can see that here. So the first row is 0, 1, 1, 0, 0, 1, 0, 1, 1, 0, 0, 1, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 0, 1, 0, 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 0, 1, 0, 0, 0, blah. Okay? Now, of course, this is even not a full representation because really it's going to be given as an array, right? So it's going to look like something like this. I'm going to quickly, well, there wouldn't be one there. Yeah, like that, right? So this is actually what it's given as, right? As this bank array, right? And then from that, you can kind of derive this thing, and then you start making pairs. So what are the rules here? Well, there's really only two rules, right? They're on different, lasers are on different rows. So that's our first rule, right? This is one of those problems where you should probably well establish what the rules are because it's really not that difficult of a problem, but you just need to understand what it's asking. Because I was actually trying to solve this problem earlier and I didn't read the problem prompt right. So I was trying to solve something that was far more difficult than what this problem actually is. So always ensure that you understand the premise of the problem because you might end up solving a more difficult problem, which is interesting to an interviewer because, well, I'm approaching a problem, right? I'm approaching a difficult problem. So look at me, I'm intelligent, but it's like, no, you didn't read the prompt correctly, right? I'm not going to hire an engineer. If I'm an interviewer and you can't read the prompt correctly, that's an indication that you're probably not going to be a good engineer. When I feed you a problem, I feed you a JIRA ticket issue, whatever, you're not gonna be able to solve it. So make sure you read the problem right, okay? So what are the two rules? The first rule is laser connect different rows. So they gotta be on different rows, right? So these two lasers can't connect with each other, right? You don't see any connection here. And lasers connect, no lasers in rows in between, all right? Now what that means is, you could say, well, okay, these two can't connect because of rule 1, right? And these two, these two look like they could reach right to each other. They can't connect because of rule 2, right? Because there's lasers on this row. So for each row, R1 less than I less than R2, there's no security devices in the ith row. So since there's a security device in this row, you say, okay, this is my R1 here, right? And this is my R2. But nothing from R1 can connect to R2 because there's lasers in rows between. Versus in this case, right, they can connect R1 and R2 because there's no lasers in the row in between R1 and R2. That's all this second rule signifies, right? And then also, the same here, right? Or no, not here and here, right? So there's kind of both examples here. R1, R2, right? There's no lasers in the rows between. Well, there's no rows between, right? So you can always connect, adjacent rows to each other because there's nothing in between. There's only this weird case where, if you want to jump a row to make R1, R2, you have to have the case where, there are no lasers on the row between. Okay, so those are basically the simple rules. So let's start walking through this and trying to think maybe if we can kind of walk through this procedurally, how are we going to turn that into code? Well, all right, let's start building these lasers then, boy. So nothing on the same row can connect. So I can connect this to here, here. That's 2, 3, 4. All right, 5, 6. So I got 6 from that first operation there. All right, now when I get to this thing, I don't need to concern myself with anything above this row, right? Because it would break rule 2, right? So the second I saw, the second I see this row here, I know that I can't connect anything there. So row 7, 8. So another plus 2. So this one gives you plus 2. This one gives you plus 6, equaling 8. And so the answer is, voila, 8. All right. So how do we solve this problem? Well, I guess the only real observation you need to make is, well, we got to keep track. So we got to keep track of, trying to keep track of R1 and R2, right? And I'm using this nomenclature here, right? Of R1 and R2. And for any valid R1, R2, for any valid R1, R2, meaning, 2 rows, because what I'm doing is I look at 2 rows, right? Right, I look at these 2 rows here, and then I try to figure out, okay, these are valid, these rows can be with each other, right? They can match with each other, and then how many lasers do they create? Well, they just create the length, the number of lasers at R1 times the number of lasers at R2. And what I mean by that is, like, when we look at here, right? There's 3 lasers here and there's 2 lasers here. So how many new connections did that make? That made 6, right? Because for each laser, you can use all the other lasers in the previous row, right? So that's 1. For each one, I get 3. So that's just multiplication. So that's 2 times 3. Right here, it's 1 times 2, so you get 2. Right, so for any valid R1, R2, I get an additional R1 times R2 combinations. Or R1, R2 lasers that I create. Right, because for each of these, I'm gonna just draw it out, right? For each of these, I can go to each of the previous, right? So for each of the ones, I can go to all the previous ones, so that's just multiplication, right? I hope you see that there, right? I could, add it out and show you, okay, for each one, then, factor or whatever, but I hope you see that's just multiplication. I multiply these things together, that gives me the number that I can create, right? So that's kind of the main observation. And, well, as soon as you encounter something like, maybe we start here. We say, okay, this is our R1 at the beginning. We can never have the same R2, right? Maybe we move this R2 down. We look here and we say, well, there's nothing on this row, okay? Then I go to the next row and I find something. And the thing to notice, as soon as you find something, I can never match anything after this point with anything before this point, right? Because the second rule says that any row in between can't have any lasers. So as soon as I find a row with lasers, I can never connect anything below to anything above, okay? And what I mean by that is, I guess, let's do like a little general example here, right? If I had lasers here, right? And then I had a system of all zeros. Set systems of all zeros, right? As soon as I find something with a 1 in it, right? Nothing below this point can connect above, right? If I had all 1s down here, for example, right? As soon as, because what happens is, what happens is, okay, you know, these things can connect to each other, right? But at this point, after this point, if any of these lasers tries to go through, it's going to hit this boundary and it can't go through, right? Because every row in between can't have any lasers. So anything below the first point of which you find a 1 can't be connected to. Okay? So what I'm trying to say here is, like, all these lasers up here, they can't get past this point because there's a laser in the way. So basically what that indicates is, well, if this is my R1 and this is my R2, right? As soon as I find an R2, none of these can ever be used again. So I might as well just shift my R1 down and then try to find my next R2. Okay, so as soon as I find a row that has lasers, nothing above it can ever be R1 again, right? That's my new R1, and then I shift down, okay? So when I look at this problem, what I do is I basically say, okay, here's my R1 and my R2. There's no lasers here, so there's no possible combination that I can get. I move down, I find 2 lasers, so I multiply my R1, my R2, I get 6. Now nothing above here can ever be my R1 row again. So now I make this row my R1 and I move R2 down. And that's just the whole process. So you kind of go down until you find a laser. You say, okay, I have lasers at this thing, multiply them together. Now that there's lasers at this thing, nothing above me can ever be used again because this has a laser, so it's creating a boundary. So that becomes my R1, and I just move down like that. Okay, so let's go ahead and do that. So what are we going to do to make this work? Let's have res be our solution. And we're going to return res at the end, and we're going to unplug my iPad because it's causing issues with compute. Okay. And then we're going to say, what are we going to say? We're going to say, we're going to look at each row, R2. So let's say R1 equals 0. Or, you know, I want to make this, look good. So let's say int. So since these are characters, we need to convert them to integers so we can sum them up, right? Because I want to find the number of lasers that I have on each level. So I'm going to say int of the laser for each laser in the first row. Right, so I'm basically saying is we're going to start R1 up here and R2 right here. We're going to say R2 in range 1 because they can never be on the same row. So you don't need to, look at R1 and R2 being the same row because they can never be on the same row, the lasers that you're creating. Length of bank. All right. Now we're going to say R2, the number of R2 equals, it's kind of weird I'm doing R2 equals R2, but whatever. Sum of, it's the same thing here. Well, I guess I could just call this row. For each row, I'd say R2 is the length of bank of R, right? Now, if there's nothing, then we just keep R1 where it's at, right? Because we can still use that R1, right? At this point here, this is R1. When we look through here and there's nothing, this can still be our R1, right? Because there's nothing in the way, so then we can continue tracking down. So if there's an R2, so R2 is greater than 0, then we add that to our score. We say res plus equal R1 times R2. And now since we found lasers, nothing above can ever be R1 again. So now the newest row is going to be our R1. And that would be it, I believe. Okay, so what is the runtime complexity of this if this works? Okay. Why is that so slow? Probably because this int thing. What if you just did L equals 1? Sometimes these little operations can really slow you down. It helped, but it didn't really. Why is it so slow, guys? Because the runtime is the same. Huh. I don't know. That's interesting. So I wouldn't really worry about this. Something I'm not doing that's making it run so slower, but it's still the same time complexity. So that's the weird thing about big O operation, right? The optimal solution here is what it is, right? MN, and you can probably prove that because I have to look at all MN elements to find out the number of lasers. Yet the time complexity is kind of slow. So something about this isn't optimized to kind of push it over, even though the big O runtime is optimal. Okay. So let's say N equals the length of bank and M equals the length of bank 0, right? So it's an M by N matrix. For time, Well, we have to look at all the rows, right, in the array. Right, we have to look at all the rows of the bank, I guess, and then we have to look at all the columns. So we look at all the rows and then all the columns. Even though there's no for loop here, right, we have to sum through. So we're basically foring through that array and grabbing all the values and adding them up. So that would be, this is M, I guess, here, N, M, Mn. So that's big O of Mn. And then for space, well, we just create this one variable, well, 2 variables, 3 variables, 4 variables, and then we update them accordingly, right? So if there's a million elements or 2 elements, we only create 4 variables. So that's O of 1 constant space. All right, guys. Hope you guys have a beautiful rest of your day. Bye-bye.